Welcome to today's lecture. I want to just continue where I left off and also just make a very quick remark about some things. Anyway, let's press on. Last time what I did was we looked at bisectorial operators, and we defined the function of a bisectorial operator for these so-called psi-class functions. So we left it. We left one statement to be unproved, which was that the point v, the point 4, that if B is reflexive, then that implies that B is equal to the kernel of T plus the range of T closure. Okay, so I started with the proof of this last time and I never got to the end of it. So let me just quickly prove that before we move on today. So let's first define a subspace B naught. So these are the U in B such that the limit as n approaches infinity of 1 minus I n t inverse exists. And then we define P B naught to B naught, a projector, by the following, right? By P of U is the limit n to infinity of 1 on I n 1 on I n minus t inverse, which is obviously 1 on I n t inverse of u. Sorry, there's u here. Okay, now this is indeed a bounded projector, right? This is a projector that's bounded in B naught. So obviously we have that. So obviously B naught is equal to the kernel. We have PB naught. So this is the PB naught can readily be checked to be equal to the kernel of T, and 1 minus PB naught is checked to be the range of T. Okay, and now the point is that, I mean, we haven't assumed reflexivity anywhere here. So where reflexivity comes in is to assert that, so when B is reflexive, what we can assert is that B naught is actually equal to B. So let me just make a quick point, a quick comment on this whole proof. So remember, for a bisectorial operator, outside of the sector, so if we say it's a omega sectorial operator, out here we have estimates of the form zeta, zeta minus t inverse bounded by some c mu. So of course the mu here is a slightly larger sector, right? So this is a slightly larger open sector. So whenever we're not in this slightly larger open sector, we have such an estimate. But the whole sort of point about this projector is that actually we are arriving towards, so 0 here is the kernel, right? Because that's potentially in the spectrum, and that's the kernel of our operator. So the point is that I have this sequence here now where I can approach the kernel, and because it's a bisectorial operator, regardless of the angle mu that I choose here for my open bisector, I have a uniform constant with which to approach the kernel. and that's really in some sense the philosophy of what's happening here, right? So remember we already saw before that if we have, before we saw that if we have the spectrum, so maybe I'll draw this here. So if we have the spectrum breaking up into two pieces, omega 1 and omega 2, that we can draw a contour around here, gamma, and then we can define a projector P of u as just 1 on 2 pi I of this gamma zeta minus t inverse of u, and this is now a projection to this subspace. But here we just have a single point and we cannot draw a contour. But what we can use is we can use the fact that we have these uniform estimates as we approach the kernel in order to project to the kernel. So in a similar vein, I mean, I should really have actually mentioned this earlier. So why is all of this possible? So why do we even sort of think of the psi-class functions and these bisectorial operators? So, yes? So the question is, why does the reflexivity give us B0 equals B? So, well, one has to prove that, right? So you have to look at the adjoint space and the bi-adjoint space and prove that. No. It's the consequence of B equals... So I'm not giving a full proof here. The main point here is to define the projector, right? In some sense, getting the B naught to be equal to the full space B is just a routine thing of that you do when B is reflexive by considering the adjoint space and the bi-adjoint space and then mucking around until you get something right. So, but the important thing here to note is the construction of P, right? That's I can't prove everything. I mean, so all of these things. I mean, it takes a lot of effort to sit down and work out the details. Yeah. Okay. Yeah. So this is to prove, right? This is be reflexive implies this. Okay. So sorry. So let me get back to the discussion about projectors. So before we saw that we could integrate around such a omega 1, and we can project to this spectral subspace. It means we can cut up the space into this spectral subspace. But not only that, it also tells us that the operator restricted to this spectral subspace is a bounded operator, and it maps back into this spectral subspace, right? That's what we had before. And so, unfortunately, I should have really said all of this between us talking about this spectral separation theorem and the psi functional calculus, because the next thing to note really from this, the next logical step to note is to recall that T has spectrum of T, T self-adjoint means that the spectrum of T, so remember this, that T self-adjoint means that the spectrum of T is real, and we have these estimates, zeta minus T inverse imaginary part of zeta is less than or equal to 1, right? That's what we proved. So these were the resolvent bounds that we had. So why do I want to really point this out? So here, let me draw a picture. So here, I mean, the spectrum of our operator is potentially the entire real line, right? So this could be the spectrum of T. But what if I do the following? What if I take, say, a contour now? Well, it's not really a contour because I haven't closed it up. So it's open here. So this is a length epsilon. And say this is also, so given two numbers, right? So give me two numbers, A and B. So let's fix two numbers. What's a color to use here? We've used red there, so maybe just here. So this is A and this is B. Okay, these are two numbers on the real line. Now I'm going to write down a curve. So call this gamma epsilon. So given epsilon, right? Given a without loss of generality, we can assume that A is less than B, and some epsilon. Define curve gamma epsilon as above. Okay, so what I'm going to do here is the width here is exactly epsilon. Okay, so we can explicitly write down such a curve. So why do I want to do this? So what I want to now do is I want to consider this following integral. I want to consider the integral gamma epsilon zeta minus t inverse d zeta. Okay, so maybe I'll call this p epsilon of u. So okay, sorry, I should have a normalizing factor here. 1 on 2 pi I. Okay, so I'm gonna still draw this as a contour integral. This is just to mean that I'm integrating along a contour, or I'm integrating along a curve in the complex plane. So the point is p epsilon is uniformly bounded, right? So this is in fact uniformly bounded by 1. Okay, well, okay, that a priori that's not true. The point is that this is now uniformly bounded for C independent. Of course, the fact that it's bounded by 1 becomes a factor later, for C independent of epsilon, right? And so why? So this is due to the resolvent estimates. Okay, so that's precisely due to the resolvent estimates here, because here I'm saying that as I approach along this direction towards this number A, whether I do it from above or whether I do it from below, this the fact that I have this imaginary part of zeta controlling the way that I approach the spectrum precisely tells me that this is uniformly bounded. And not only is it uniformly bounded, I mean, this integral, I can take, this integral is uniformly convergent then, right? So I can define P of U as being P, well, I should really say, okay, so I should really say here that this is AB, right? AB. Maybe I should write AB here, just to. So PAB here is precisely equal to the limit as epsilon tends to 0 of, so I'm going to define it in this way. Now the point is this, the point is, so in fact, PAB is precisely equal now to the spectral measure that we talked about before for the operator restricted to this interval AB. In fact, this gives you a very explicit construction of the spectral measure, right? So typically when one talks about the spectral theorem, maybe you want to use something like the Rees representation theorem or something, as we talked about earlier on, to try and build the spectral measure. But this gives a very concrete way that shows the way in which these resolvent bounds can allow us to actually define a projector. So this is a projector. This is a projector. So of course one has to prove that. But the point is that this allows us to now construct the spectral measure. So the motivation in part towards looking at this more general functional calculus or these more general operators like the bisectorial operators, using the self-adjoint operators as a template, in part is really contained in this calculation that I just did now. Okay, so it's kind of a weird order to put it in because this should really have been motivation. But anyway, I've said it now. Okay, so with that, let's move on to the topic today, which is fractional powers. So before we saw fractional powers for self-adjoint operators, but let's try and do them now more constructively and more generally, right? In fact, this will be of significance to us in due course. So for this, we let T be omega sectorial, right? And can allow omega to be just less than pi for this discussion, right? And let alpha be a positive number, okay? Now, let f alpha of zeta be the function zeta alpha on 1 plus 2, 1 plus zeta 2, and this is the ceiling function, right? So I'm going to take an integer just above alpha. So certainly this is going to now be a psi-class function in S mu naught, right? Because we've because this is the cut plane, right? We haven't included pi, so it's in the cut plane, and so this is now a bounded holomorphic function. Okay, now let's define the fractional power. Now I'm going to define the fractional power T alpha as equal to 1 plus T 2 alpha. I can never get this ceiling function right. Times f alpha of t. Okay, so f alpha of t defines a bounded function, right? Because it's a psi-class function, as we talked about before, this defines a bounded function of t. So this is so f alpha of t is a bounded operator. But of course the t alpha is not, right? So what's the domain here? So the domain is equal to the u in B such that f alpha t of u is in the domain of t to alpha. Okay, so maybe I'll have to move this a bit. Oops. Okay, so that certainly defines a fractional operator. So now let me. Well, it's the domain of the composition of an operator, right? If you have operators A and B that are unbounded, the domain of the operator is precisely the U in the space such that B of U is in the domain of A. Yeah. So this is, so just remember that was what we talked about in the algebra of unbounded operators, okay? So, the remark here is that the exponent alpha, 2 integer alpha, right? So the only reason I did this is so we can get an integer, so we know how to take powers of this thing. Can be replaced by any integer greater than alpha. Of course, then we would have to replace it both here and here, right? So in some sense, this you can see from the impression of the expression that we have 1 divided by the operator down the bottom, and we are multiplying by 1 of the operator here, and then the fractional power that we want is contained here, right? So what we feel here should be true is actually true. Okay. So So proposition. Okay, so T alpha is alpha omega sectorial if alpha is in 0, 1. Yes? No, because it's reflected in both f alpha of zeta and it's reflected in T2 alpha, right? So now you're saying that it's the so now your function here f alpha also changes, right? So think about just the case of this being an integer number. So suppose that I want to define t squared, or if I have t squared. So, and then I choose my alpha to be 10. Sorry, I replace this exponent by 10. Then I'm also replacing the exponent here by 10, and these two things cancel out. Do you see what I mean there? Okay, so maybe let me just write this down, right? Maybe let me just write this down. So remark 1, remark 2. So let say alpha equals 2. So we wanna construct the second power, which we already know, right? So then I'm going to take and let f tilde alpha of zeta now say equal to zeta squared on 1 plus zeta to 10 to the 6, right? Just to choose a large number. Okay, this is certainly a psi-class function. But now now what am I looking at? I'm looking at 1 plus t 10 to the power of 6. And then I'm looking at f alpha tilde of t. So this is actually really equal to 1 plus. So remember, this is an omega sectorial operator. Because this is an omega sectorial operator, 1 plus the operator is invertible, right? Because that's, I mean, the value -1 is in the resolvent set, right? So then this is an invertible operator. So what this is exactly equal to is this is equal to 1 plus t 10 to the 6 t squared divided by 1 plus t 10 to the 6, which is equal to t squared. So does that answer your question? I mean, the point is that the two functions have to be balanced. You cannot change the exponent in the f alpha and leave the exponent in the factor out the front here unchanged. If you're changing something in the f alpha, you have to also change it here. Otherwise, of course, you muck up the domains. Yes, but first of all the powers of t do not have the same domain. The point is that you're asking here not for u in the domain of 2 alpha. You're asking for u such that f alpha t of u is in the domain. So if I change my exponent here to be something, the zeta to be very, very large, then the u in the, so now I'm looking at the f alpha of t acting on something, and I'm asking that to be in the domain of something else, and that's where they cancel. Yes, good. Okay, so so back to the proposition. So T alpha is alpha omega sectorial if alpha is between 0 and 1. The second thing we get is that if alpha is less than beta, then the domain, so this is related to what was just asked, domain of T beta is less than the domain of T alpha. Okay? Third thing, T to the alpha plus beta is equal to T alpha T beta. And then we also have, even though we get unbounded functions here, so it's not always that we get spectral mapping theorems, but actually in this case we get that the spectrum of T alpha is equal to the spectrum of T to the alpha. And the last point is that if a bounded operator now commutes with the resolvent, then S commutes with the fractional power. Okay? All right. So example. So earlier we saw that T non-negative self-adjoint implies that it's 0. Well, so let's take a function. Let's take something that's non-negative self-adjoint. So this is now we know is 0 sectorial, right? That's already an example that we've seen. And so the point is that we saw how to using spectral theorem, T to the alpha can be defined. This exactly equals the construction here. So there are a number of ways to prove that. I already mentioned that we could access the spectral theorem by a contour integral as I demonstrated before. But actually, yes, the spectral theorem says that non-negative every self-adjoint operator has a measure called the spectral measure for which is projection valued so that the operator can be recovered in some way by integrating against the measure. Yes, that was a very important. That was a very important theorem. That was the prelude to discussing fractional powers before, when we talked about fractional Sobolev spaces. Yeah, that's so. Yes, we have discussed this in detail. Okay, so anyway, we saw how fractional powers for non-negative self-adjoint operators can be defined before, and that's what we did when we came across the fractional Sobolev spaces. But now, the thing I'm asserting is that this construction is consistent. There are a number of different ways of seeing this. There are also approaches to these functional calculi which are more axiomatic, and one can show that if you have a certain functional calculus of operators, so that resolvents can be recovered, and certain other things can be recovered through the functional calculus in some systematic way and related back to the original operator you started with, then every functional calculus has to be, so any two functional calculi that satisfies these axioms have to produce the same thing. But I don't want to go into such a treatment here. So this can more or less be verified through this contour integration that I talked about before. Okay? But I just want to point out here that, these are unbounded operators now when we typically get the fractional powers, but we obtain them. So the whole point of this procedure is we obtain them through first going via a bounded operator and then multiplying by an integer power operator that gives us the right cancellation. Okay, so I just wanted to give a very explicit construction of that. The second thing I want to really quickly talk about now is the heat equation and semigroups. So again, we're in the world of sectorial operators. So the first thing that we need for this is the following theorem, which is called the convergence lemma. So in fact, it's the Macintosh convergence lemma. So we have T omega sectorial, and we have B being a reflexive space. And suppose that we have some psi n, which are psi class functions, such that there exists some constant, so that these psi class functions in the L infinity norm are uniformly bounded. All right, uniformly in N. Okay. So if we now have, we have some f in the holomorphic functions. So these are, okay, so I haven't, okay, so maybe I'll just write, holomorphic S mu naught with such that psi n converge to F uniformly on, so whole infinity, compact subsets of S mu naught. Okay, sorry, what am I doing here? This is the wrong thing. Sorry, that's not what I want. Sorry about that. Okay, so now the point is that we have an omega sectorial operator, and we have reflexive space, and we have a bunch of a sequence of psi class functions here that converge, that are bounded uniformly in N. Okay, so so what do I want to do with this here? So so let me just think now. So what's the best way to say it? So now suppose that suppose psi n converges to some psi uniformly on compact subsets of S mu naught. Then we have that the psi n of t, psi n of t are a Cauchy sequence. Okay, sorry, that's what I wanted to say. Okay, so so that's the first thing I want to say. Then let's consider now for omega sectorial operator. Let's consider the heat equation, right? So we want to solve dt minus t of u equals 0 with u naught. Well, we have to make sense of what we mean here by u naught, right? So we're saying that the limit, the b limit of t tends to 0 of u of t is equal to some u naught in b. This is not within the theorem. This is, the theorem conclusion is that the psi and t are a Cauchy sequence. Okay, so we want to consider this heat equation. So we want to solve this equation with this initial data. So the idea now is to construct semigroup. So we want to construct a function of this operator, and the semigroup is e to the minus t capital T of u naught, right, as the ut. Okay, that's what our candidate solution is. So our solutions are generated by this semigroup, right? So how would we do that? So the first thing to note is that the map zeta to e to the minus t zeta. So this satisfies e to the okay, so e to the minus t zeta is now bounded by some constant. So I should say not t zeta here, e to the minus zeta here. So this satisfies c of zeta to the minus alpha, right? For basically all alpha. I mean, this is trivial, right? This is for alpha positive, right? I mean, it decays exponentially. Yeah, decays exponentially. But the problem is e to the minus zeta approaches 1 as zeta goes to 0. Okay, so we're not in the psi class as we would like to be in order to take a function of this. But what we can do is the following, right? We can instead consider the following operator. We can consider, so define, or let psi of zeta equal e to the minus zeta minus 1 on 1 plus zeta. Okay, so this is certainly now a function that, well, it goes now to 0 as zeta goes to 0. So this decays polynomially both towards 0 and towards infinity. All right, so so now this is certainly a psi class function. And then we define e to the minus tt as being equal to 1 plus t t inverse plus psi of tt. Okay, so again you can impressionistically see what's happening here, right? This is really, I mean, we can take a function of this, but what we really expect is this term to be 1 plus t to the inverse if we chuck in t here. So everything, again, just like in the expression that we had before, everything nicely cancels out. So now the proposition is as follows. So the proposition is that when B is reflexive, T is omega sectorial, so there exists a constant such that e to the minus t capital T is uniformly bounded by this constant, right? For all t in 0 to infinity. Okay? It is a semigroup. So this is, so in particular this is a bounded operator, right? In particular, e to the minus tt is a bounded operator for t positive. Okay. So the second thing is e to the minus tt, e to the minus st is equal to e to the minus t plus st. Okay, that's a semigroup property. The third point is that t maps to e to the minus tt. Well, this is what I've already said before. So this is a continuous map. Okay, so that's easy to see. A very important property where the convergence lemma, where this is why I wrote down the convergence lemma, is we can try and differentiate this operator. So to differentiate this operator, what we actually require is precisely this convergence lemma, right? Because we need to, we approximate by these difference quotients, and we need to know that the operators that we get out of considering the difference quotients are precisely, well, they're going to be compact on, they're going to be convergent on compact subsets, and so we have a Cauchy sequence, right? So we need to know that. So this is negative t e to the minus tt e to the minus t, right? Another very important property is what happens on the kernel. So remember, we have a reflexive space here, so we can split up the space into the kernel of the operator and the closure of the range. Okay, so if u is in the kernel of t, one second, then e to the minus tt of u is equal to u. Yes? Yes. 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 The question was, are the bounded operators on a Banach space a Banach space? And the answer is yes. The other important property, so the reason I'm writing this down is because the heat equation is going to become really the central object in what we're going to do. Okay, so for elliptic operators, in boundary value problems, it's really the heat equation that governs everything. So we'll see that in time to come. So let me just be very careful and write down all of these properties. So if we're in the kernel, then the action of the semigroup is constant. So now for a general u in B, we have that e to the minus tt of u goes to 0 as t goes to infinity, and e to the minus tt of u goes to u as t goes to 0. Okay, so this is an approximation to the identity. Okay, another thing, so suppose that u is in the domain of t. Actually, this happens if and only if the limit as t tends to 0 of 1 on t e to the minus t t u minus u exists. And in this case, negative t of u is equal to lim t tends to 0 of 1 on t e to the minus tt of u minus u. In fact, this is an important fact for any semigroup, right? So this is how you would extract out what we call the generator of the semigroup. And you would do that by trying to understand when this limit exists, and then you can extract an operator if you define the semigroup in a more axiomatic way. Okay, but yeah. And the last property I want to point out is the following. So S is a closed operator now, commuting with a resolvent this implies that S commutes with e to the minus tt. Okay? Okay. So now I won't prove this. These properties come out of the wash once you just define this object here, and then you just have to calculate with it. So now the point is, let's return to heat equation. So fix some initial U naught in B. Yes, just 1 second. Let me just write this down. And define U of t as e to the minus tt of U naught. Then, it's readily verified that dt minus t of u equals 0, and the limit as t to 0 of u of t is equal to u naught. Yes, question? Mm-hmm. The question is, don't I need 1 minus what? What you don't need that 1 divided by t is in the resolvent set. What you need is negative 1 is in the resolvent set. Because if negative 1 is in the resolvent set, so what is the resolvent? It's zeta minus t. So negative 1 minus t is invertible, is the same as 1 plus t being invertible. So now if I scale the operator t by a subscript t, so you need to know that you mean when you say 1 divided by t, you mean lowercase t. Yes, so you definitely need 1 divided by t's in the resolvent set, but you have that, right? Because here we're always working with a sectorial operator, not a bisectorial operator. So it's in the cut plane. The negative real axis is always in the resolvent set. That's of paramount importance. Of course, we cannot do this for bisectorial operator. So the question is, if it weren't the case that we were working with a bisectorial operator and some other kind of operator where we might still have some access to 0 via some, I don't know, if it's bisectorial or something, well, the problem then is that, of course, you could do that and you can try and define such an operator. But then the point is that e to the minus zeta is not going to be bounded uniformly, right? Because if you have too much negative real bits here, this thing is going to blow up. So yes, you can do it, but then you're not going to really enter the realm of bounded semigroups. You're going to be in the case of maybe unbounded operators, and then you have to examine that case very carefully. But you could, of course, the power of a functional calculus is you can just write down functions of operators and you can muck around and try and understand them. Yeah, thank you. Yes? Mm-hmm. No. I mean, why is it a problem if you have the Banach space R? Because, I mean, of course, it depends on how you define the Laplacian, right? For me, the Laplacian would have positive spectrum. So with positive spectrum, then I have to take e to the minus t. Of course, if your Laplacian is div grad rather than negative div grad, then of course then you take e to the t, e to the tt. Yeah. Okay, thank you. So anyway, it's readily verified we have this. So another thing I want to really quickly point out is this idea of this being an approximation to the identity, right? So the proposition is, again, we're in the realm of B being reflexive. I'm going to write this just for repetition. T is omega sectorial. Then B, I'm going to call it B infinity T, which I'm going to define by the intersection of all powers j equals 1 to infinity of dom t to the j, which is a subspace of B, is a dense subspace of B. Okay? i.e., if U is in B, then e to the minus tt of U is in B infinity t, and e to the minus tt of U converges to U. Okay, that's your approximating sequence. So a priori, we don't know that the intersection of all of the powers of the domains of a sectorial operator, I mean, it could be non-empty. It could be empty for all we know, right? It could be zero. So we find that not only is it non-zero, it's actually a dense subspace. So what's the proof? So the proof is let f subscript k of zeta now be equal to zeta to the k e to the minus zeta. So this, we don't have to worry. This is actually a psi-class function. Okay, this has the right decay. And the point is, and so fk of t now is a bounded operator. Okay, and it's uniformly bounded, in fact, right? But fk of tt is equal to tt to the power of k e to the minus t. And the fact that it's a bounded operator, so the fact fk of tt is bounded implies that B is equal to the domain of fk tt. And what's the domain? This is precisely going to be the U in B such that e to the minus tt of U is in the domain of, well, tt to the power of k, right? So that means that e to the minus tt of U is in the domain of t to the k, so little tt to the k is the same as the domain of t to the k as a set, and k is arbitrary. Therefore, e to the minus tt of U is in the space that we defined, and it is dense since e to the minus tt of U converges to U as t goes to 0. Okay, so again, you know, it looks like we've done something very abstract. How is this helpful? So, so far, when we have done things, particularly in the manifold context, when we have done things like mollifications, we have always used, you know, we've gone into some trivialization and we have mollified by pulling everything into this chart through using cutoffs and then using the standard symmetric modifiers in the Euclidean context. But here is a way to try and do this in a very global way without resorting to that, right? So let me give you an example. So let M prime be compact without boundary. Okay? And let E be any Hermitian bundle over M, and nabla any connection, and the Laplacian being nabla star nabla, right? Closure, say. Okay. So now I'm going to take a U in L2 of M prime E, and note that by proposition, e to the minus t of nabla of U is now in the intersection of j equals 1 to infinity dom Laplace to the j. But this is precisely equal to j equals, so by elliptic regularity, we know what this domain is. This is the Sobolev space H2j M prime E. But then this is contained in the smooth functions, or the smooth sections. So immediately in one stroke, we can find a smooth approximation to U, starting with U in L2, simply by the application of this semigroup method. Okay. So of course we're going to have to use this for other reasons later, but I just wanted to show you a quick example that we're not just straying off the path for no reason. So, there are very powerful applications by using this heat method. Okay, so now we're really going to move on. So hopefully I want to finish this today, this stuff on the functional calculus, so that next time we can move on to really trying to analyze the operators that we're interested in. So let's now move towards, so the title of this section when we started was the H infinity functional calculus. So far we haven't really seen a full functional calculus, because with a functional calculus we should really at least be able to take one of the functions. So we should be able to define the constant function 1 and take one of the operator. So let's now, in our discussion, let's restrict. So we can do this in Banach spaces, but it becomes more technically cumbersome. So we restrict now to B equals to H, right? The reason I talked about fractional powers and the semigroup is actually we don't need a full functional calculus to even talk about these things. We can discuss them in great generality, but in what's to come next, we need something more. So we restrict now to be to the case we're in the Hilbert space. So now let's have a look at a definition. So if T is omega bisectorial, so now we're back in the game where omega is less than pi on 2, and there exists some constant such that psi of T is uniformly bounded by psi infinity. Okay? Then we say that T has an H infinity functional calculus. So we have to still justify what we mean by this, right? But psi is so this is for all psi in psi, I should be more precise, right? And I should then say, okay, so let me just erase this. Yes. Has an H infinity functional calculus. Okay, so the question there was, or the surprise there was, 1C for all psi. But it's not all psi, because here you're controlling the norm here in psi also. Okay, so remember, so let me make a remark about that. So we always have psi of t is less than or equal to some c depending on psi and t. Okay? So now the point is, now what we're asserting is, here we are saying that c psi t has an additional structure. I.e., c of psi t is controlled in a particular way. It's controlled by some constant c, which, you know, comes from t, say, and this dependency on psi is precisely the sup norm of psi. So it's not saying that it's independent, that there's one constant for all psi. It's saying that the constant that we get in the bound is controlled in a particular way for each psi. So of course the dependency on psi is still here. Okay? So now we have a lemma which is the second Macintosh convergence lemma. This is the second one. So suppose T has an H infinity functional calculus. Okay. It's okay. Actually, before I state this lemma, let me make a definition first. Sorry. So let's define. Let me define H infinity of S mu naught. These are precisely functions f which are defined on S mu union 0 to C, bounded, such that f restricted to S mu naught is holomorphic infinity S mu naught. Okay, so we're allowed to have a jump at 0. These need not be continuous at 0. They can jump at 0, right? That's what I'm... No, it doesn't. The open closed bisector does not contain 0. The closed one does, sure. Okay, sorry, I should say here this is a function on the open. Sorry, that's correct. Yes, it's not the closed here, it's the open, right? It's defined on the open bisector, but including 0. Okay, so suppose that T has an H infinity functional calculus. Often we just abbreviate it like this, right? Because the mu is not so much of a concern. Typically we take the mu to be slightly larger than the omega. Then, for all f in this H infinity S mu naught, so maybe I should say it here just to be precise, at least at the start, functional calculus. Then for all f in this H infinity space, there exists some Fn which is in the psi class. Fn converges to F uniformly on compact subsets of S mu naught, and Fn of T is a Cauchy sequence. Okay, so this is a very important lemma. so what happens here is that the kernel, the zeroth part of this operator, we have to treat exceptionally. And so now we're in a place to define a full functional calculus. So definition, oops. We define ft of u. So if t has an h infinity s mu naught functional calculus, then for f in h infinity s mu naught, we define ft of u. So the first thing is we have to peel off the kernel. So f at 0, we can take a value there, right? It's a bounded thing. But now we project to the kernel of t along the range. Okay, so this is the projector that projects to the kernel, and it's 0 on the range, right? So we first project. So that takes care of the lower order term. And what happens now is that, of course, the remaining part is so if we have the psi-class functions are really, they're going to map the range to the range, right? So what we have then is we can define limit n to infinity. So these are psi-class functions now, which are Cauchy, and we just take this limit. So this is the part that's going to map to the range. So, okay. Remark. It is easy to verify that f of t is independent of fn of t. Okay, so if we, fnt of u. Okay, so maybe I have to write that here too. fnt of u, right? So it's a Cauchy sequence in the strong operator topology. Okay. Yeah, I think it does for u in B. U in H. So in the previous lemma, I also made that alteration. I shouldn't have skipped that. Okay, so let's quickly just say some things about this. So the first thing is that f maps to f of t is now really an algebra homomorphism, right? Because 1 is contained in that. So this, from S mu naught to the bounded operators of the Hilbert space, is an algebra homomorphism. Well, actually, I won't say it that way. I'd say, yeah, because we want to assert that. So this is a homomorphism. Yes. Sorry. Independent of the sequence Fn. Yes. Okay. The second thing is that this is now bounded, right? So this has a bound just like before, with the constant now coming from the constant that we have in the assumption of a H infinity functional calculus. The third point is that, so these are the properties: alpha f plus beta g of t is equal to alpha f of t plus beta g of t. F g t is equal to f of t g of t. The constant function 1 acting on t is just equal to the identity, and the map zeta maps to 1 on Z maps to 1 on zeta minus Z acting on T is equal to 1 is equal to zeta minus T inverse when zeta is in the resolvent set of T. Okay, well, sorry, shouldn't say resolvent set, that's wrong. When zeta is not in S mu naught, right? We have to be careful with that. Yeah, but I don't want to say that. I want to explicitly write this down. So maybe even not say homomorphism. This is a bounded, this maps us into the bounded, so yeah, maybe this is a better way to say it. So F mapping to F of T maps us into bounded operators, right? What do these bounded operators satisfy? Well, their bound can be controlled in a very explicit way. Oops. The bound can be, because I want to explicitly say what it means, right? I don't want, it's true it's an algebra homomorphism, but I want to explicitly say what are the properties that it satisfies, because actually these properties in 3 that I've written really is axiomatic for functional calculus, right? Having 1 of T mapping to the identity and this resolvent mapping to the resolvent as we expect, really fixes it. It makes a functional calculus unique. So I want to just really point this out explicitly. So first of all, the first assertion is that for each F, it lands us in the bounded operators. The second assertion is that the bound is now controlled in a very explicit way. The third assertion is the homomorphism property. Okay? And the fourth assertion is the way that it commutes with operators. So it's in the bicommutator. So if S commutes, so S is a closed operator on H, commutes with zeta minus T inverse, then that means that S commutes with F of T. Okay? All right, so now comes the very deep theorem. So unfortunately, this is not a course on functional calculus, so I can't get into all of the details, right? But we will see how to use it. So theorem of McIntosh, the following are equivalent. 1, T has an H infinity functional calculus. 2, there exists a psi in the psi class functions. Not identically 0 on either sector, right? So the sector S mu plus minus naught, satisfying 0 to infinity of psi t, psi little t t of u squared dt on t is comparable to u squared. So let me move this here. For all u in the range of T closure. Okay, so this is a very important estimate, so I'll put a thing around that. And then the third equivalent condition is that for all psi in the psi class, not identically 0 on S mu plus minus naught, star is satisfied. So these estimates are known as, these estimates are called quadratic estimates. Okay, so this is a very important theorem because it gives, so up until this point, the functional calculus looks very much like a qualitative object, right? So we have some estimate, maybe that we want to know is satisfied, and then we want to deduce certain things from it, but it doesn't give us a real clear criteria on how we might prove such an estimate. And what these quadratic estimates really allow us to do is to access functional calculi through being able to localize the problem in some way, right? And the main point here is that the parameter t appears here. So even if you take a local chart and you look at an estimate like this in a local chart, the point is you see the operator at both 0 and at infinity, meaning that you see the spectrum, because I mean you can think of that local chart as being something like a window, and then you're moving this operator, the spectrum of this operator basically right through this window from the low frequencies to the high frequencies, right? So these psi's, so let me just make a very quick remark. So if these were real functions, the size would look like this. So the size would look like this, and when I write here psi of t zeta, this is really the frequencies of this so it's really okay, so maybe I'll write psi t of t. This is really saying that I'm really focusing on the frequencies of the operator t around the real, or near the real part 1 on t, right? So this is like 1 on t. And when we have these functions, what we get are functions like this, right? So in some sense, this is very harmonic analytic, right? So it's really saying, so what we can see is, so just to give an impression of what's going on. So the idea here is see psi t of u as a bandpass filter for a spectrum of t around the real part, so the real part, for the real part of the spectrum of t centered around 1 on t. And what this estimate is saying is that actually we can chop up. So if we look at u as a signal, right? So this is a bandpass filter by seeing u in h as a signal. Okay, so what we're really doing is we're chopping it up and then we're pasting it all together, and we're able to reconstruct the signal up to a constant in norm. And that's really what this estimate is saying, right? Of course, in the kernel, nothing happens. The psi of t on the kernel is 0, right? So that's why we have to peel away this kernel. But away from the kernel, on the range, we're able to reconstruct the signal. I won't say anything more than that. You can try and read up on this stuff, and this connects to Calderon-Sigmund theory and real variable harmonic analysis. There's a massive sort of area surrounding all of this. But in the remaining few minutes, I want to just say a couple of more things. So let me first give an example of the quintessential psi-class function that we're going to look at. So let me look at zeta plus psi plus minus of zeta equal to 1 if the real part, the plus minus real part of zeta is positive, and 0 otherwise. Okay, so of course this is chi plus minus is certainly in h infinity of s mu naught. I mean, it can, because we can allow it to jump. We can allow it to be discontinuous at 0. Okay, and so from this we also have a signum function. So the signum function of zeta is just chi plus of zeta minus chi minus of zeta. So now if t has h infinity s mu naught functional calculus, then chi plus minus of t and signum of t are bounded operators. Okay. Moreover, we have that t restricted to, so these are projectors, right? So what I've written here, the chi plus minus, are projectors. So these are projections which take us from chi plus minus t back into chi plus minus t, because since t trivially commutes with its own resolvent, right? So this is a closed operator that commutes with its resolvent, and so we have that it commutes with the functional calculus. So the Macintosh modulus, so then modulus t, the Macintosh modulus is t signum of t, is an omega sectorial operator. Okay, so what is this plus minus of t? So if we have a bisectorial operator, then the point is that, so chi plus is 0 here, chi minus is 1, and chi plus is 1 here, and chi minus is 0, right? So what it allows us to do is it allows us to project to the, so this is really a projection to the spectral subspace to the left and right of the complex plane respectively. Okay? So, okay. So that's the example that I want to give. That's the end of the example. So now I want to sort of think about how we, alternative ways we can get to bounded H-infinity functional calculus, because this is really going to be the central thing that we need in studying boundary value problems. So the first thing I want to say is the following. So I should have maybe written this in the fractional powers section. So the first thing I want to point out is that so instead of a omega bisectorial operator, we have an omega sectorial operator. T is omega sectorial. Then the domain of t to the alpha we can obtain as the domain of t h theta equals alpha for alpha between 0 and 1. Okay, so that's the first thing I want to say. The second thing I want to say is how we can now connect fractional powers of operators and the H-infinity functional calculus. So this is another very important theorem. So this is due to Pascal Aucher, Alan McIntosh, and Andrea Nahmed. So suppose that T is an omega sectorial operator. Not bisectorial, omega sectorial. So an omega sectorial operator has an H-infinity functional calculus if there exists alpha, beta positive numbers such that the domain of T alpha is contained in the domain of T adjoint alpha with the estimate T alpha of u less than or equal to, or along with some constant, T star alpha of u, okay? And domain of T star of beta is contained in the domain of T star of beta here with T star of beta of u controlled by T of beta of u. So I have to include the estimates here as well as the domain containments, right? Because if the domain containments usually just say that as Banach spaces they're bounded. That means with lower order terms. Here, these estimates are homogeneous. And that's very important. And so the point here is now that if from other reasons we can find that plus minus t is a bounded operator, and the modulus operator now has an h infinity functional calculus, then t has a h infinity functional calculus. Okay, that's just putting things together. So why is this? So we haven't seen a proof. I've been jabbering a lot and I haven't shown a proof. So if we let psi be so psi is a psi class function, say in S mu naught. So the point is that psi of t now can be written as psi of modulus t signum of t, right? So signum squared is equal to the identity. So we have this following thing. So if chi plus minus is bounded, so is signum, because it's just a difference. And so we can obtain this as psi of modulus of t signum of t, right? And so chi plus minus of t being a bounded operator then means that psi of t of u is comparable to psi of modulus t of u, and we know that this is bounded by psi infinity when we take a psi class function. Okay. So, I know I'm just maybe going to go over time just by a couple of minutes, but let me just finish now. So I'm about to finish, so just with a couple of examples. The first one is T is self-adjoint. Oops. T is self-adjoint implies that this is a non-negative self-adjoint operator. So here we have that the chi plus minus are bounded by other considerations, but we also have that domain of T star is equal to the domain of T, right? Because T and T star are equal. So in particular, we can apply this theorem of O'Shea, McIntosh, and Namad, which implies that modulus T has an H infinity functional calculus, and that also means that T equal to T signum T has an H infinity functional calculus. Okay, so every self-adjoint operator has a H infinity functional calculus. So we've achieved our goal of having a functional calculus that includes the self-adjoint operators as a special case. So now let me just finish with this one last example. Pardon me for going a couple of minutes over. So let's take a compact manifold as before with non-empty, with boundary that is empty. And let's take a differential operator of order m. And just for the sake of application, let's assume that the kernel of the closure of the operator is 0, right? So the L2 operator, and it's bisectorial and bisectorial. And we're going to further assume that the chi plus minus, so in application, this is what we'll find to be true. So the spectral projectors are bounded in L2 of M prime E. Okay? So the point now is that D prime is invertible, is now invertible and bisectorial. And so what does this allow us to assert? So elliptic regularity says that so the domain of D is equal to the domain of D adjoint. That's good. And actually we have that the domain of the modulus of D, which is just equal to, and since D is equal to D signum of D, so this is a bounded operator which commutes with D, so they have the same domain. So I should say here this is equal to HM, right? So this is equal to HM M prime of E, and so because of this, and signum of D commutes with D, I should put bars, then the domain of D bar is going to be equal to the domain of D bar adjoint. And this is again HM M prime of E. But now we said that D is invertible. And because D is invertible, what we have is that U, which is in the HM norm, this is comparable now to U plus D of U. This is the inhomogeneous norm, but invertible means I can absorb this norm into the operator. So this is now comparable to D of U. That's very good. And furthermore, we also have, because the signum is bounded, this is modulus D of U. And similarly, we have U, HM is comparable to D adjoint of U, because that's just another order M differential operator, which is invertible. And remember the spectral theorem, the theorems that we have regarding where the resolvent of the adjoint, how that communicates with the resolvent of the original operator. So if D is invertible, then the adjoint is also going to be invertible, because 0 being in the resolvent set means that the conjugate of 0 is in the resolvent set of the adjoint of D. Okay, so now again we can apply theorem, and from that we obtain that both D bar and D has an H infinity functional calculus. Okay, so I will end here, because from next lecture onwards we're going to apply all of this to differential operators and explicitly see where the H infinity functional calculus enters the game. Thank you. Questions? Mm-hmm. That's true, because I wrote it wrong. Should be that. Sorry. So the idea is that we have to have some numbers so we can control the domains of the fractional operators with respect to each other. So alpha and B can be different. In application, of course, so in application here, when T is a self-adjoint operator, alpha and beta are both taken to be 1. And actually, that's a general theme that we'll find for differential operators, right? Because when we have a differential operator, at least on a compact manifold without boundary, we have elliptic regularity. That allows us to talk about the domain of the adjoint of the operator, and these two are going to be the same, right? Oh, sorry, in this example, I forgot to say that this is elliptic. I'm really sorry. So this is elliptic. Of course, if it's not elliptic, we cannot argue in this way, right? The point here is that this is an elliptic operator, and that's where I use elliptic regularity here in the to equate the domains with HM. Anything else? Okay, so if not, let's meet next time and continue.